Our senior design project consists of designing a whiskey distillery and the fermentation process. Here, you can see a schematic of our project which highlights all the components. We chose to focus on a modified shell and tube heat exchanger. Our presentation will tackle the modeling of a heat exchanger in 3D using MATLAB. In practical engineering, most heat exchangers are controlled autonomously. In order to understand how a temperature controller will work, it is beneficial to understand the underlying theory behind how temperature changes. Therefore, we developed a MATLAB simulation of this phenomenon and hope to further students' understanding of thermodynamics behind a heat exchanger. Inputs are the physical constants such as density, heat capacity, thermal conductivity, and the initial conditions that are temperature, pressure, and velocity. The outputs are steady-state values which will remain constant over time. In this schematic shown, we have the pump where the water flow is coming out at some velocity and head through piping causing frictional loss. It then goes into the fermenter with a coil heat exchanger. The coil is made of copper tubing and modeled as a helical wound. This causes it to cover a range of surface area. We can assume that the hot water flow inside the pipe is fully developed and also assume that the density won't change since the temperature variation of water is very small. As shown, the system is analyzed at 2 points. With each point having a specific velocity, pressure, and height, the Bernoulli's equation can be used to find specific values. Using the pipe size, material, along with elbows and fittings, the head loss can be calculated. By calculating head loss from the pump to coil, we can get an idea of what the initial conditions will be for our analysis. These conditions will later be used to model the behavior of a Newtonian fluid in a pipe with heat exchange. In the model we will be presenting to you in the next few minutes, we will be modeling only a small section of the heat exchanger. There are many simplifications that have been made to make the explaining a bit easier. However, the general underlying fundamentals are all the ideas we've been exposed to in the past. To start off, one of the basic principles required for this project is the Bernoulli's equation. It is a conservation of energy principle appropriate for flowing fluids. Being one of the most used equations in fluid mechanics, it is derived from integrating Euler's equation between 2 points. Euler's equation states that for an inviscid fluid, the change in momentum of a fluid particle is caused by a body force and the net pressure force. Integrating it allows to obtain values at specific points for the process. Bernoulli's equation relates pressure, kinetic energy, and potential energy of the system. It is important to keep the restrictions in mind when considering to use this equation. It only applies to steady, incompressible, frictionless flow along a streamline. In our case, and in any real-life scenarios, the frictionless flow restriction is not met. To allow the energy to change, a head loss term is added to the equation. Head loss accounts for a sum of major head losses due to frictional effects in fully developed flow in constant area tubes, and minor head losses resulting from entrances, fittings, area changes, and so on. These head losses can be calculated separately.
The next equations that need to be used are the Navier-Stokes equations. These are the governing differential equations for the motion of flowing fluids, which take into account temperature, pressure, density, viscosity, and velocity. The Navier-Stokes equations are composed of equations for the conservation of mass, conservation of momentum, and the conservation of energy. Along with Bernoulli's equation, these are the most famous and used equations in fluid mechanics. The first of these equations to consider is the conservation of mass, which is shown with a continuity equation. This shows that the mass and the control volume can neither be created nor destroyed, so that the mass flow difference throughout a system between the inlet and outlet streams will be zero. Looking at the equation, you can see that the sum of the partial derivatives of the x, y, and z directions are equal to the velocity multiplied with the gradient operator, which is equal to 0. The next equation is a conservation of momentum. The first equation shown is for incompressible three-dimensional flow using density, velocity, viscosity, and the gradient operator. This equation is derived from Newton's second law of motion and eventually into what is shown in the first equation. The simplicity of this equation is due to the density of the fluid being accepted as constant, and the next system of three equations is for each dimension x, y, and z. These are the differential equations for fluid motion satisfying the continuum assumption which states that fluids can be treated as continuous even though they are composed of molecules. In these equations, P, Vx, Vy, and Vz are unknowns, where a solution is found by applying the continuity equation with boundary conditions. The last of the Navier-Stokes equations is for the conservation of energy, also known as the first law of thermodynamics. The simple form of the energy equation shows that the change in energy is equal to the sum of work and heat entered into the system. The expanded form of the equation is a complex partial differential equation. This equation consists of three main sections. The left-hand side of the equation represents the energy being dispersed through the medium, which is the water inside the coil of the heat exchanger in this case. The second section of the equation is phi v, which is the amount of energy lost in the system. The third main section of the equation is the section where K, the thermal conductivity, is multiplied by the second order partial derivatives of temperature in the x, y, and z directions, which is the conduction section. Next are QC and QR, which represent convection and radiation respectively. In this equation, since the heat exchanger, the water inside it, and the mash being fermented are all in contact, and since there is such a small temperature difference between the water and the mash, the radiation will be assumed to be negligible.
When it comes to heat transfer in this particular 3D simulation, conduction and convection are the two phenomena that are being observed and accounted for in our model. The basic form of heat conduction equation is obtained by applying the first law of thermodynamics. The energy balance for the differential element can be written as shown. In our 3D simulation call, we assume that the cross-sectional area is a perfect square. Therefore, Cartesian coordinates are being used. The first term in above equation represents the rate of heat energy coming into the element at x, y, and z planes. The second term represents the rate of heat energy coming out the element at x plus dx, y plus dy, and z plus dz planes. The third term represents the rate of heat generation inside the element. A medium conducting heat energy might involve the conversion of mechanical, electrical, nuclear, or chemical energy into heat energy. In our case, for example, heat is generated in an exothermic chemical reaction in a medium which involves the chemical reaction of yeast with the simple sugars. The reaction might also be endothermic reaction. In such case, the heat generation term will become a negative quantity. One thing to note is that heat generation is a volumetric phenomenon. This means that heat generation occurs throughout the body of a medium. The rate of heat generation may vary with respect to time as well as position within the medium. While conduction is the transfer of heat energy by direct contact, convection is the movement of heat by actual motion of matter. It is the energy transfer between a surface and a moving fluid with different temperatures. In reality, this is a combination of diffusion and bulk motion of molecules. Near the surface, the fluid velocity is low and diffusion dominates. At distance from the surface, bulk motion increases the influence and dominates. Convective heat transfer can be forced or natural. Our model accounts for only free convective heat, neglecting the other one, for simplicity. Implemented in our model, and it calculates the heat transfer by multiplying the specific convective heat transfer coefficient of the medium by the temperature differences between surface and bulk fluid.
So the 3D expansions and simulation development for the Navier-Stokes. For the simulation that we developed, we used the steady-state assumption in order to simplify our calculations significantly. As you know, when things change with time, the amount of computational power that it takes actually explodes. So therefore, we wanted to try to keep things simple by keeping the steady state going. For any simulation development, it can be broken down into 5 different steps. The first being defining a global variable, especially when there are multiple variables to take care of, like for example, velocity and temperature. Then you have to develop the general algorithm, which will be applied mainly to interior points. However, it can be applied to the boundary and initial points as well. Next is to discretize all of the equations, which is the most time-consuming part of any simulation development. However, if you make it past this, then you can move on to apply all the initial and boundary conditions. and then you can start running the simulation. However, for the purposes of this presentation, we'll be not showing the simulation proper, just because it can take upwards of 20 minutes to run. So we are going to instead show our proof of concept model, which is a highly simplified version of this that is only heat transfer through a block of material. Keep in mind this isn't exactly Navier-Stokes. However, it is still applicable to the overall system. So, the global variable, if you remember from numerical analysis, is how you keep track of multiple variables in one single matrix. For 2D, where, for example, change of temperature in the y direction and x direction, you have the 2D case of the global variable. However, once you move into the z direction, you need to have 3 different vectors, I, j, k. So in order to access all of the new layers of m that you need to add in the third term of the global variable, which is k minus 1 times n squared. There is also a variable of there is also an algorithm for decomposing m back into its ijk. However, we're not going to go into depth about this. We will show you a code that does it, but it's not the focus of our simulation. So next is the general algorithm. In the general algorithm, there is a lot of bookkeeping that you have to do. So it is extremely important that you don't miss any equations or variables. In fact, we have 5 equations. So since we were already developing an n cubed system, now with 5 equations, we have 5 times n cubed, which makes the problem only get much larger very quickly. So our 5 equations are our continuity equation, the one momentum equation for each dimension, x, y, z, and the overall energy equation. Now, if you remember from numerical analysis, you have your first derivative and second derivative centered finite difference forms, which you can see on the screen. However, these are only applicable to systems where you only change in one direction. So now, just to see if you understand, using what you can see, can you figure out what these subscripts actually should be? So the correct answer would be that you multiply each of these subscripts by 5, and then you subtract the quantity 5 minus the equation number. So for example, continuity is equation 1, so 5 minus 1 is 4. Therefore, yn plus 1 would become y 5m minus 4 plus 5. So it's a little complicated, but don't worry. You do it once, it's like riding a bike. Next is the discretization. Now, as I've mentioned before, we have 3 directions now, x, y, z. So if we use the global variable, we can actually keep track of each one of these very easily. That being said, it's still very difficult to keep everything together. And so when you start to write all the residuals, you start getting code that looks like this. Now, keep in mind, this is only the beginning part of the code. This isn't even taking into account the actual residuals yet, but you're going to see those very shortly. So don't worry, you're going to see why the Navier-Stokes is such a hard thing to code. So next up, applying the initial conditions. Our equations will require a large number of them. However, we can still simplify even more. So let's say that the initial velocity is only in the z direction for this example, and that that's at 1 meter per second. We'll also assume, for example, that the temperature is uniform at 330 Kelvin inside the pipe. And finally, we can make the assumption that, well, actually, we can solve for this. We can solve for what our initial pressure would be, dependent on our initial velocity. So using the formula that you can see on the screen here, can you solve for our initial pressure in pascals? Well, the correct answer, you can see on the screen now, would actually be just shy of 101,000 pascals. So the pressure won't be too much different from an atmosphere. However, it's still important to note that this change in pressure is there. So now we're going to build the simulation. However, as stated earlier, we won't be showing the true simulation, as it would take way too long to run, and it would completely eat up our time for the presentation. However, we do have our proof of concept model ready to go. So I said earlier that I would show you a quick little function that would do the global variable. Here it is. It's very simple to do. In reality, it only takes about 7 lines of code. So it's a really easy thing to do, and it's a good thing to have in your tool belt. Then you have your decomposition algorithm, which is a little more complicated. However, it's still not that hard. And if you figure out how to do this, then you can switch back and forth from your global variable to 3D coordinates with relative ease. So if you want this, take a picture, because we're going to have to move on to the rest of the code. So the picture from earlier that showed the beginnings of the residuals, this is the rest of them. So get R1 is the code for the continuity equation. R2 through 4 are the momentum equations for x, y, and z. And the energy equation. And the energy equation, in my personal opinion, is the hardest one to code, mainly due to the phi sub v term. If you would like, in your simulation, you can just assume this away. You can just say that it's 0. However, you would lose the dissipation of heat due to friction and its own viscosity. So you have to be careful when making this assumption. It might not be significant sometimes, but it is definitely helpful to have to accurately model the system. So here's our proof of concept. We took the heat equation, simplified it a little bit, and then decided that this was going to be the equation that we're going to do. We're going to take the del squared of t, add in the change in t with x, and set it equal to -2. So now we're going to show this proof of concept in action, and hopefully you can follow along. Is this code right here. Now this is actually the answer key to the homework, so if you don't want to do everything on your own, this is a very good way to get a little insight as to how we approach the problem. So our code takes into account this massive residual on line 35. In this residual, there is a lot of terms. However, each one corresponds to a different direction. Anywhere that's plus or minus n squared is in the z direction. Anywhere it's plus or minus n is in the y. And anywhere plus or minus 1 is in the x. In the Jacobian, same thing. M minus or plus n squared is in z. M minus or plus n is in the y. Plus or minus 1 is in the x. Same kind of deal as we had in numerical analysis. Now, if you notice here in line 50, we actually don't have it just adding in del. We have del being multiplied down a little bit. That's just to make sure that it converges to an actual value. Otherwise, it tends to not converge to the same value each time. So we have it being overdamped a little bit just to make sure that the value is stable. So if we run this code now, I'm just going to quickly type in xf equals problem solve 3D solution, and then run. And if you'll notice, down here, this is at the bottom of, or the back of the simulation space. This is a little closer to the front. This is even closer. And you can see that over toward the left is where we have a temperature of -1, which means that that is the direction to where heat is going. And you can also see that it's skewed a little bit down toward the front of the simulation. So that shows that the heat is actually flowing also preferentially towards the upper rows, which is where x equals 0, which is a part of the code that we defined. And with that, everybody, are there any questions?